thing we could ask is, what are exponents? And what exponents are is, sorry, one moment, let me just get my um, drawing pad real quick. So if you can recall, exponents are kind of the small numbers on the top right that you would usually see with the number. That kind of indicates what power is a number. And when we talk about powers, we kind of refer to how many duplicates there are for that certain number. So when we say that, for example, 4 to the second power, what we really mean is there's two fours being multiplied to each other. And that's kind of the basics of what exponents are. Roots are kind of exponents in disguise, but rather than with whole numbers, they're actually in fraction forms. So one very common kind of root is what's known as a square root. And it's the simplest form of roots in math. And if you're wondering what the symbol for a square root is, it often goes in the form of this, which is the square root of, let's say, 25, for example. This is what is known as a square root, this kind of line right here. And that kind of means whatever's inside the number, you need to have two of it in order for it to come out on the outside. So it's kind of hard to explain here, but I'll kind of go through it right here. So 25 is another way of saying 5 times 5. Now because there's a pair inside, what I can do is take that number to the outside of the square root here, and it'll turn into 5 here. That's why often when you associate with square roots, square root of 9, for example, you would know that it's 3 right there, or square root of 4 as well. So this is kind of how we would do square roots as well. If you don't have one that's a perfect square like these ones, you kind of see what can go outside in the first place. So if I was talking about square root of 40, for example, what I usually want to do is get it to the most prime numbers that you can get, numbers that you cannot divide anymore. So square root of 40, if you can kind of put it into a tree right here, it can also go like this. 10 and a 4, and then they can go down even further, right? Into 5, 2, 2, and 2. So square root of 40 is another way of saying 5 times 2 times 2 times 2. And then your goal is to look for pairs that can go to the outside. As you can see, this pair of 2s right here can go to the outside. And that is kind of how you can deal with square roots there. So here are some examples of the following here, or for square roots. So I didn't really mention it earlier, but square roots are technically, as I said, exponents in disguise here. So when we talk about 25 to the 1/2, think of this also as square root of 25. And the reason being is because of how this power works out here. If we have some kind of general term, a to the b over c, what's going to happen is that kind of power fraction is going to translate to whatever kind of root it is along with the power in there. So that c would be on the outside, which dictates what kind of root it is, whether it be a square root or a cube root or whatever kind of root it may be. And that b will represent the power for the letter or for the variable a. So that is kind of how that little bit of research or background on how that power works. So that is why we can also say square root of 25. You might also refer to see it as SQRT, and then the number inside, which is the same exact thing as well, square root 169. And then maybe occasionally some people will put the number just to confirm that it's a square root right there. And then we kind of saw it earlier. That's how the square root would be for 25. So thanks for joining us, Kyle. How do you feel with square roots so far? Do you feel kind of confident with how roots work and how to solve things that are in radical form? Okay, I'll try to go through everything here. This one is talking about square roots at the moment. So if you're kind of familiar with this, then you should be kind of all good. If you have any questions, just say it at any time. So yes, this is some of the many ways that square roots can be identified as 25 to the 1/2 power, or FQRT 169, which is a short way of saying square root, or in its regular form, right here. So square root of 25, like what I did earlier, you kind of want to put it into the smallest numbers possible, or prime factorization, and turn it into this 5 times 5. Find some pairs, and you can see what goes on to the outside. And you'll see that square root of 25 becomes 5. So square root of 169 is kind of no different as well. And if you notice, these are all known as perfect squares, which means that they can perfectly turn out to some kind of integer in the end, or a whole number there, without it being some kind of decimal somewhere out there. So square root of 169, it's kind of hard to really see it, but there's a way that I've known it, and this would actually have turned out to be 13 times 13. And that would be the pair for that as well. So you would see that the pair of 13 times 13 can go to the outside. So square root of 169 would be 13 in the end. And then we also have negative square root of 81 here, which would mean that that negative is on the outside and the square root is on the inside, 81 here. So there's something to keep in mind here about negative numbers, but I'll go through that right after this. You can see that with negative 81, that can turn out to be 9 times 9. And usually you'd want to factor it out even further, but coincidentally we have these big numbers right here that are a pair on its own. So we can also just take those pairs together and turn this to be negative 9. If you were going to put it out even further, you'd eventually come out to the same answer as well. So there's a big difference when we talk about negative square root of 81 and square root of negative 81. Do you know what happens if the inside number is negative, Kyle? Close, close. It won't really be talked about in this lecture here, but hopefully it won't also be on the test. But what happens is, this is what is known as an imaginary number that comes out. So I'll just go through it really briefly because it's not so important. What would happen is, if you have some kind of negative number inside a square root, what's going to happen is this imaginary number will pop out to signify that the inside number is negative. Because technically, you cannot have any negative number inside of square roots, because there will be no answer in the first place. So in order to compensate with that, this negative I is what's known as the imaginary number, and this indicates the square root of negative 1 here. This is so that you can still kind of solve the answer, but it will signify that this is an imaginary answer in the end. So just a little fact, just a little thing to throw in there, in case if that kind of comes out. So what would happen is, this will still be 9, but you also have that imaginary number, which is I, 9 times I. Or you could also see it as 9 times square root of negative 1. So yeah, just a little thing to throw in there. But throughout this lecture, we won't have any negative numbers inside radicals, so don't worry too much about that there. We can also, kind of talked about this already, but you can also find the roots by factoring the radicand, which is the number inside the radical. So I'll point it to it right there. So that's what's known as the radicand, if you haven't noticed, or if you didn't know. So yes, this is the radicand, and this is the radical. So I think I did show this earlier, but yes, as I was saying, roots by factoring or finding pairs, the way that I did it as well. So if you want to find the square root of 72, you can try to find, or you can kind of like factor out this radicand here, find the smallest numbers possible, and see what you can work out from there. So 72 is another way of saying 8 times 7, or 8 times 9. And then you can factor it out even further to see what kind of pairs they are. So you have 3 times 3 from 9, and 8 you have 4 times 2. And you can go even further with the 2 times 2. So here's all the numbers that make up 72. It breaks down all the way to 2 times 2 times 3, or one more 2, times 3 times 3. And you can put that in a calculator and you'll see that it comes out to 72 again. So 2, 4, 8, 24, and then I believe that's 72. So the next goal is to find out the pairs. Like I said, just looking for pairs that can go to the outside. So you see this 2 times 2 can go outside, and this 3 times 3 can also go outside as well. And by going outside, I mean that it goes right outside of the square root that we have here. So we have the 2 times 3 here. And remember, it's important to know that only one of them goes outside instead of 2 of them. You find a pair to make one of them go outside. So that's why it would be 2 times 3 square root of whatever's left in there. And as you can see, this 2 was left out, so that would stay on the inside right there. So in the end, we say that radical 72 can also be, in simplified form, 6 radical 2. You kind of see how we got that answer so far? All right, awesome. So if we can real quick, do you think you could kind of solve the square root of 2000 here? It's probably going to be a bit of a while, but I'll kind of work with you there. If you think you found the most simplified form, just let me know. So I'll do it out my way in case if you have another way. So we know that it's square root of 2000 here. I'll see if I can do this the quickest way possible so that I don't have a really long tree. But what I'm seeing is 100 and 20, and then we could put those down even further. I'll put this as 25 and 4. 4 times 25 is 100. 20, we can have a 5 and a 4. Other things you can kind of look for is like perfect squares, which is like, for example, 25, 9, 81, or even 100 as well. Perfect number or perfect squares are the ones that I talked about, where you could easily factor them out like this. Where like square root of 100, you know, obviously equals to 10. Or 49, square root of 49, you know that it would be 7. But if not, just look for pairs in the end if you don't really know the perfect squares. So we can keep going from there. You see that you have a pair over here, a pair over here, and another pair over here. So here's all the numbers we have here. 2000 turns out to be 5 times 5 times 5, and then you have 4 2s as well. So another way you can kind of put it as is 5 to the 3rd power times 2 to the 4th power as well. And then what you can kind of see is you had 2 pairs of 2s and another pair of 2 right there, and you also had a pair of 5. If powers are kind of hard to see here, I can also do it like this. If you see that you have a power of 2 for them, like this for example, 5 to the 2nd power times another 5, and then we had a 2 to the 2nd power and another 2 to the 2nd power. You can take out this 5, take out this 2, and take out this other 2 as well. And then they'll all go to the outside in the end here. So that's another way you can kind of see it as well. So on the outside, you have 5 times 2 times 2 square root of whatever was left there, which was 5. And that simplifies all the way to 20 radical 5. Did you kind of get a similar answer or kind of a close process of how I got this? Okay, awesome. So I think you're pretty good with these. I think you might be a little confident with the roots by factoring. Do you think you can also do it with variables? It's kind of the same exact way. It's just that there's more letters and less numbers. So I kind of go through it from here as well. So you can see here with the 1/2, that's also known as the square root, just as I said earlier. But with the 1/3, that is what is known as the cube root of the 1. So rather than finding pairs, now you have to find triplets in your answers. So that's how you can do it from, that's how you can kind of tell from there. If you can kind of guess with 4, if it was to the power of 1/4, you'd have to find pairs of 4, or rather quadruplets in the root over there. So that's another way you can kind of see if you have to look for pairs or triplets or whatnot. So we'll start off with the square root right here. So this whole thing is going to be square rooted in the end. So we'll be solving that from there. So another way to look at it is 16 times x to the 8th power times y to the 6th power. So if you can also find an answer before me as well. So what will happen is we're going to look for pairs in here. And there's many ways you can look for pairs here, as I said. So let me kind of split up the 16 to emphasize what pairs there are. We had a 4 times 4, right? And then I'm going to split up those x's so I can do it in the method where you had like x to the 2nd power, so there. Do you see there was x to the 2nd power there? And what I'm doing with these x is I'm just basically splitting up those exponents there. In the end, all your exponents should kind of add up to x to the 8th power in the end. So as you see here, we have x to the 2nd power, 2nd power, 2nd power, 2nd power. They would all add up to x to the 8th power in the end. And the same thing with y to the 6th power. And then you can kind of guess how many x's and y's can go out. So we have this 4 times 4, so we know that that pair will go to the opposite side. You see, we have lots of x squares here, so we have 1 pair, 2, 3, 4 pairs of x's here. So what goes out is an x to the 4th. And then we see we also have 3 pairs of y squared. So in the end, there will be 3 pairs of y going to the outside. So that means our answer in the end would be 4 times x to the 4th times y to the 3rd power. How do you feel with that answer? Do you kind of get how we got the answer here? All right, awesome. So yeah, cube roots, or the third root right here, is no different than the second root. Just instead of finding pairs, we're going to find triplets now. So I'll erase this work up here so I have more space to solve it. So whenever it's not a square root, they'll often associate the root with some mini number right over here. And that number over here is going to be 3. So whenever there's no number here, you can always assume that it'll be a square root there. But if it does have a number such as 3 right here, then you know it's not a square root. So that's what we're going to see here. 8x to the 8th power, y to the 6th power. And in case if you were confused with the powers, I can just break this down into a bunch of numbers into here rather than it with being powers. So I'll show you what I mean. This 8 can turn to be 2 and 4, and then turn out to be 2 and 2. So you know that it'll have 2 times 2 times 2 in the end. So 2 times 2 times 2. And then the x, you know there will be 8 x's. So I'll kind of just write this out to emphasize the triplets to find. So x times x times x times x. That's 4 x's so far. That's 5. That's 6, that's 7, and that's 8. And I don't think I'll have enough space for the y, so let's see what I can do. 1, 2, 3, 4, 5, 6. Okay, I have just enough space there. But you get the point. There's 6 y's and 8 x's. Remember that our goal was to find triplets to go to the outside. So I'll start off with this one right here. We know that for the 2's, we have a triplet right over there. So 1, 2 will go on to the outside. My question is now, how many x's would go to the outside? Would there be one x? How many? Okay, another question to say is, how many triplets can we successfully make? Don't worry if there's any leftovers. So how many x's can go to the outside? Awesome, awesome. So yeah, glad you're understanding that so far. So yeah, we have one triplet right here and another triplet here. So we still have remaining x's, but we only have 2 x's left, so we can't really make a triplet there. So yes, 2 x's will go outside, otherwise an x squared. And then we can see with the y's, they make 2 perfect triplets, right? Y to the third power and y to the third power. So we can get 2 y's outside as well. Y to the second power. So the only leftovers we have, just to emphasize that, is the remaining x's right there. So in the end, we'll have 2 times x to the second power times y to the second power cubed root of x squared. And that can be your most simplified answer right over there. So yes, glad you're understanding this so far. So it's not, powers aren't so bad when you really get the hang of it right there. So whether you're trying to find pairs or triplets right there, it'll be relatively easy when you can kind of get a visualization of how to do it. So yeah, let me know if you have any more questions with that. But with that being said, do you think you could kind of simplify this one over here and this one? Let me know what you get for your answer there. Yeah, so we'll start off with this one first. Let me know what answer you get for this. Okay, awesome. We'll see if I get the same answer as well. There are kind of quite a lot of rules that there are with roots and powers, and I kind of did glaze through them as well. But one of the rules for this one is that square root of 18 times square root of 16, they can be combined together as one radical if the radicals are the same. There's a bit more complications if there are different radicals there. But yeah, this could also be turned down to 18 times 16. So we'll see what we get from there. I didn't really have to do that, but it kind of makes it easier to emphasize that these can be radicaled out easily in the end into one full radical. So I'll dictate to see if that's the correct answer. So 16 turns into a perfect 1, which is a 4 times 4. So that's one pair going outside. 18, we have 9 and a 2. And that 9 has a 3 and a 3. So 1 3 will go to the outside as well. Our leftover is the 2. So yes, you're correct. 4 times 3, which is 12. And we have that remaining radical 2. So good job on that right there. Awesome job. So I think you're pretty confident with numbers. Do you think you could do it with variables as well? Try it out and let me know what answer you'll get there. So yeah, good luck. All right, we'll see if it's 6x squared here. So, like I said with the last one, you can combine those two together to make one full radical there, if the radicals are the same. So yeah, 12x to the third power times 3x. And they can be combined like terms to make it look kind of simpler, which would have been 36x times x to the fourth. So we'll see that this turns out to be two pairs of x here. You can kind of notice an x squared and another x squared right there. So yes, so far we know that two x's are going to be on the outside. Now with the 36 there, this is actually a perfect square as well, which would have been 6 times 6. And if you were to put it into small numbers, in the end, you'll have numbers that would come out to be 6. So yes, you're correct there. Nice job on that, Kyle. So do you have any questions so far? Any other confusions with radicals so far? All good with it? Awesome, awesome. So we'll go away from multiplying it to the exact opposite. which is dividing 2. But with this one right here, even you can simplify this. I think what I've kind of mentioned earlier is that you can combine them together into one big radical. Whichever feels better for you, you can just keep them separate or put them together. So yeah, this is a little more complicated multiplication of radicals here, especially with it being a cube root and 2 variables here. So I'll kind of guide you through this one here. So this turns out to be square cube root of x to the 5th, y to the 2nd power. Combine that with the other one there. So that 5 stays outside, whether or not I'm combining it. So with my goal of combining it, that 5 would stay outside. So we have cube root of x to the 5th times y to the 2nd power times 8 times x to the 2nd power times y to the 4th power. And then, like I said, you can combine like terms so that you can see how many that you can have. So we got 8 times x to the 7th power times y to the 6th power. And then with our goal here, we know that this is a cube root, so we're going to find pairs of 3 instead of pairs of 2. So you can kind of put it out in whichever method you have, but you'll eventually find out that there's 2 triplets for x to the 7th power. You have x to the 3rd, x to the 3rd, and then you have that remainder of 1 random x there. They all combine to make x to the 7th power. So we know that 2 x's would go outside. With the 8, you can see that there would be a 2 times 2 times 2. So this 8 would turn out to be 2 in the end. So far we have x squared and a 2 on the outside. So it's not too bad, not too difficult. It's just an additional variable added here, which is the y to the 6th power. And we can see that there'd be 2 triplets there, which is y to the 3rd and another y to the 3rd, or y times y times y. And you'll see that 2 y's will go to the outside. So in the end, you're just left with all of these and 1 remainder of x on the inside. So your answer would have been 2x squared y squared cube root of x right there. And that's how you can get your simplified answer. So whenever they say simplify, the kind of translation basically means put as much variables and numbers as you can on the outside. And that's how you would simplify these kinds of radicals here. So now we're moving on to dividing radicals. So we're going to try to simplify this one here. And rather than multiplying it, we're going to divide it. Now, dividing and multiplying is almost no different than with regular fractions that you would cancel out with. So I'll show you what it means by here. So we have the square root of 8x to the 4th power, y to the 8th power. That one's on the top. On the bottom, we have square root of 16x squared times y to the 4th. Now, there are 2 ways that we can actually do it. But first, I'll go with this method first. We're going to simplify at the top and the bottom first, before we can figure out what can be canceled out. So we'll look for pairs on the top. I'll kind of pace through it faster than usual, but if you have any questions, let me know. So I can see a pair with the 8, because in 2 times 2 times 2, 1, 2 would be left on the inside. 1, 2 would go, 2 pairs of 2 will go outside. X to the 4th, you can see that there would be 2 pairs right there, so there will be an x squared. And then with the y to the 8th power, you can see that there will be 4 pairs going outside, so we'll have y to the 4th power. So we'll have 2x squared, y to the 4th on the top. And on the bottom, we'll see that we have 4 on the outside, we'll have x on the outside, and we'll have y squared on the outside as well. Everything is used in the radical, so there'll be no leftovers. And then now we can just cancel like terms here. So this 2 over 4 will just turn out to be 1/2 on the bottom, top and bottom. x squared can be canceled out with x here, so we'll just have 1x on the bottom. I'll just get rid of that 1, turn it into an x. We'll have y to the 4th cancel out with y squared here. So that will be y to the 2nd power on the top, with the leftover there. And I won't have whatever's left there, which is just that radical 2. So that's your most simplified answer that you can get with this equation, or with this radical. You kind of see how I got those answers there? Any confusion? Okay, awesome. Yeah, it's kind of just a little additional step compared to multiplying radicals, because first we simplify the top and bottom separately, and then we figure out what can cancel, so we can simplify it even further there. Yeah, think of it as 2 multiplying radicals and the simplifying fraction, 1 in the end there. And then that's where you can get your simplified answer. So, with that being said, do you think you could try this example here? Try it out and let me know what you get. Okay, we'll see if I get the answer. Let me kind of brush it up just to confirm if this is the answer. Is that x, y, cube root of 3x, y times y? Oh, cube, yeah. All right. So we'll see if I got that answer from there. So, like I said, we'll have to simplify the top and bottom first to see what can cancel out. So we'll have a simplified cube root 24. So just to briefly see real quick, 24, and we have the 8 and the 3. We'll see that we have a triplet with the 8 with the 2 times 2 times 2. So we know that we'll have a 2 on the outside and a leftover 3 on the inside. There is no triplet for x because there's only one x, which means that'll stay on the inside. And last but not least, we have the y to the 4th. One triplet will go outside, while the last triplet stays inside. So we'll have 2y right over there. And then, similarly with the bottom, we'll have 2 coming out from the 8, which provides a triplet of 2's. And we'll have the y stay inside because there's only one y. So we can start off with what cancels out. We have the 2 here that comes out. And we're left with y to the y outside there. But we're not really done here. So this doesn't happen too often, but we can actually cancel this out even further. So this is where I'm going to talk about the second method. So what would happen is if the roots are the same, for example, if they're both square roots or cube roots right here, what you can kind of do is combine them into one full cube root and turn it into a fraction like such. So what would happen is this. We have the y still on the outside, right? But now we have this big cube root, which kind of engulfs the top and the bottom. That was inside it. So on the top, we have the 3xy, and on the bottom, we have the y. So now you can kind of see what can really cancel out here. And I was just trying to prove the y's would cancel out here. So you'd actually be left with y cube root of 3x in the end here. So if you can kind of see with what I did here, you can actually do it from the very beginning as well and kind of treat it as a fraction in the end. So 24xy to the 4th, and then we had 8y, right? You can immediately start canceling out some stuff, such as the y to the 4th and the y on the bottom. And the 8 and 24, which I believe would be 4 something, right? 12 over 4. And I can cancel out more to become 3. Yeah, there we go, 3. That's how I was going to math. So we see we get a cube root of 3, x, y to the 3rd. And that y can go outside because it's a triplet. We'll have y cube root of 3x in the end. So whichever you feel like is more comfortable with you, I suggest you go with whichever path is possible for you. Just as long as it's the correct kind of rules to get. So yeah, you can do it this way or this way in the end here. Whichever feels more comfortable. So that's with that example here. We'll go with adding radicals. So there's a simple rule, which is kind of easily mistaken as for radicals. With radicals, it's not like multiplying radicals where you could simply combine the same radicals. What's going to happen is you treat that radical as a radical that can only combine with the same ones. So, in other words, I cannot combine square roots of 5 and square roots of 7 when they're added together. But I can combine 6 radical 5 and radical 5 because they have the same radical. Kind of imagine this like they're different kinds of terms. A radical 5 and a radical 7 is the same term. However, it's not the same term. But a radical 5 and a 6 radical 5 is the same term. If you'd like as well, you can also treat it like it's an x. y, or something else. This is like a 6x right here, and this is just an x. So you can see that those would combine together. 3 and 2 are regular integers, so they can combine together. 6, 4, and 5. We can't really combine anything with radical 7, so it just stays put. And this radical 5 will combine with that 6 radical 5 to form 7 radical 5. Similar to how if you had x and 6x, it would have been 7x in the end. So yeah, that's kind of a simple way to see how radicals would combine. So you cannot combine the same, or you cannot combine different radicals, but you can combine radicals with a similar number inside, similar radicand inside. Same thing would be with subtracting radicals. So just as long as they have the same radicand inside, or same number inside, you can combine them together. So if there was another thing right here, like a radical 12, you cannot combine that with anything else. So the simplified answer would have been 2 radical 13 in the end. So yeah, that's how it would work out. So kind of straightforward, a little easy to remember, but kind of hard to forget because there's a lot of ways you could kind of get confused with it. So with that being said, do you think we can simplify this by any chance? Very close, actually. One could think that they could put this x to the third on the inside and have this y to the third on the inside, and then it would look like x to the fourth, y to the fourth, plus x to the fourth, y to the fourth. And that is actually incorrect here. And this is mostly due to the rule when you try to put numbers back inside a radical or a root. So what happens is, if you were to put a number back inside, you kind of have to double the number that goes inside. So let's say, for example, if I wanted to put this 2 back inside, I would have to actually put 2 times 2 inside, a duplicate of its own. So this would have been 2 times 2 times 2, which would have been 8, radical 8 in the end, square root of 8. And then you can kind of put it back in to place, and you'll see that it would have been 2 radical 2. So that is one rule you have to keep in mind with putting those numbers together. But in simple cases, you'd see that because of the inside, they're not actually the same. You have xy to the fourth power and x to the fourth power times y. And those are not the same roots in the inside. If they were actually the same, xy to the fourth power and xy to the fourth power again, that's when you would combine them together. As such, for the coincidental next problem here, which has some same numbers and some different numbers. So it's important to know what can combine here. So just to confirm, can I combine this term right here with this term right here? 4 cube root 5a minus 3, or cube root of 3a. Awesome. So yes, that's correct. How about this 3a with this 5a over here? Would I combine them as well? All right. Okay, so with process of elimination, you can see that this 5a can only combine with the 2 cube root of 5a right there. That's because they have the same numbers and variables inside there. So yeah, only when they have the same exact numbers inside, they'll be able to combine. So we have 4 cube root of 5a minus 2 cube root of 5a. So just the outside numbers get subtracted, so it turned out to be 2 cube root of 5a minus cube root of 3a. And that is the simplified answer right there. So just to make sure, can I combine the numbers if it was like this? Square root of 2a plus 4 square root of a times 2. Can I combine those two together? Yeah, that's actually a trick question. So the order does matter, or doesn't matter too much in this case here, and I'll kind of elaborate on that real quick. So briefly, this can also be turned into 2 times a. So that is one thing that some people might get confused with, is that people will, some of the problems may look like they can't combine, when in actuality they can combine here. So a times 2 is almost another way of saying, but literally another way of saying 2 times a. Likewise, x times x, cube root of x times x, plus cube root of x squared can actually combine as well. So those are some things to watch out for in case if they kind of throw something like that. So in the end, this will still turn out to be 2 cube roots of x squared. So yeah, just make sure that they can be combined together from there. So yeah, most likely they'll be simplified already, so we'll see from there. So with that, we'll move on from roots and go on to quadratic equations. And quadratic equations, we kind of touched upon this quite a bit back with trinomial functions. So when we're talking about the standard form for quadratic equations, we're referring to this equation kind of like this. The standard form often goes with ax squared plus bx plus c here. And then often we would have it equal out to 0 right there. So this would be the standard form for quadratic equations right here. So when we write it in the standard form, typically we want one side equaling to 0 in the end here. So if we want to rewrite the following form in standard form here, what we want to do is move this 3 to the left side here. And in order to do that, we would have to subtract 3 to both sides. So we see 5x plus 3x squared plus 6 minus 3, which will give 3 in the end. But this isn't in fully standard form. We kind of want it in the descending form of the powers of x. So first up would have been x squared, or in our case here, 3x squared, and then the 5x, and then the 3, and then you'd see that it would be 0. With that being said, can you kind of quickly identify me what is A, B, and C here, corresponding to this one right here? So what is our A, B, and our C? Okay, awesome. So yes. So we would see that A, more specifically, would associate with the number before the x squared. So these are the correct answers right here. A would equal to 3, so you see the number before x squared. B would equal to the number before x, which is 5. And then 3 would be the lonely number without an x. Oh, sorry, I kind of messed this up right there. There we go, plus 3. So yeah, it would be the number without the x there. So that's our A, B, and C right over there. So that's how we can put quadratic equations into a standard form. So one quick example here is that we would want to rewrite this equation into standard form here. And I'll briefly go through this right here. So there are a couple of ways that you can do this, multiply this out. So we have 2 times x plus 3 squared, or other words, a duplicate of it, right? Minus 5x equals 6. So what happens here Not too sure what method that you have here, but the way that I would do it is that I kind of create a box and I kind of multiply out the terms that we have here. So we have an x squared plus a 3x plus 3x and a 9 here. So that's what this would turn out to be here. Minus 5x equals to 6. So I'll kind of solve through that first because this would be the harder part right there. So we see that turns out to be x squared plus 6x plus 9 there. If you have any questions, let me know from there. From there, I would have to do the distributive property here, and we'll get that 2 into each and every term right there. So I'm going to put this whole thing up here real quick and out of space. We would get 2x squared plus 12x plus 9 right there, minus 5x, which equals to 6. So now that we have it all out of the parentheses and out of this squared here, we can kind of combine like fractions. And if we want, we can also just subtract 6 to both sides already so that we can get it to its standard form. So we can see that we have a minus 6 in there as well. So I'll combine with the squares first. There's really nothing else besides the 2x squared, so I'll just leave that as b, 2x squared. Dealing with the x's, we have a 12x and a negative 5x here. So we can put that as 12 minus 5, which is going to be 7x. And with the numbers without the x, we have 9 and negative 6. So that would turn out to be 3 equals to 0. And from there, you can figure out your a, b, and c right there. And then if you can look at it at a glance, you see that a would be 2, the one with the x squared. B would be 7. And C, the lonely one, would have had 3, would be 3. So yeah, that's how we can get it into standard form. Pretty kind of straightforward right there. Just try to get it as factored out as possible, or unfactored out as possible. And then turn it into the standard form right over there. So yeah, with quadratic equations, we're going to talk about what is known as the quadratic formula. Does that kind of sound familiar to you, the quadratic formula? All right, awesome. So I don't have to give you the complicated equation there. But very briefly, I'll tell you what the quadratic formula is. What happens is you got to get into its standard form first, right? And that's where you put the a, b, and c terms into use. So that's why we've been talking about that. So with that quadratic formula, you'll be able to find any x as long as it's in that standard form. Right over there. Very complicated equation there. But if you can remember that, it is relatively easy to use there. And this plus and minus sign signifies that there will always be 2 answers there. And that is often signified because we have this x squared right over there. So we can solve that using the quadratic formula here. And you'd eventually come to find out with the a, b, and c terms. We'll start off with what they are first. A equals to 1, that indivisible 1 right over there. B turns out to be 4. And c is actually negative 5. That's signified because we have a minus 5 right over there. So we can see that really quickly with the quadratic formula, we have negative 4 plus 4 minus square root of 4 squared, which is 16, minus 4 times 1 times 5, or negative 5, and we'll turn that into a positive number right there. So 4 times 5 times, 4 times 5 would be 20. So all over 2 times a, which is just 1. So we'll have 2 right there. So we can see that it would have been 36 right there. And square root of 36 would be 6 right over there. Over 2. And now we could kind of cancel out some numbers there from there. And we see that x could either be negative 2 minus 6, or negative 2 plus 6. So that's how you can get your answer for x right there. So yeah, just kind of briefly going through that because we're running out of time there. So we can also use the quadratic formula to solve the equation there. And if you want, Sherry, would you like to take over because we're almost out of time? Or should we just go through this problem real quick? How do you feel, Kyle? Would you like to kind of end it from there, or do you have time to solve this one problem? Okay. So if you'd like real quick, you don't have to give me the simplified answer, but if you can, just plug in the quadratic formula from there. If you can find your A, B, and C, then you can just plug it into the quadratic formula, and I'll let you know if that's correct. So yeah, like I said, put it in standard form, and work from it there. All right, awesome. So let's see if that is the simplifying, or if that's the standard form there. So x squared minus 2x. I'm going to put 6x to the left side because I like my numbers on the left side more. So we see that'll turn into a negative 8x, and we're going to actually add the 16 there. So that's awesome. Great job right there. So you can see what our A, B, and C will be eventually. So A is 1, B is negative 8, and C is 16 there. With the quadratic equation, you'll see that you have the negative B. Because there's a double negative, it would be positive 8 plus or minus, let me just move this a bit, plus or minus square root of B squared, negative 8 times negative 8 would be 64, plus 4AC, 4 times 1 times 16, all over 2 times A, which is just 1. So we'll just have 2 there. Eventually, you can solve it from there. You can figure out what that quadratic or that radical is, and then you can simplify with the 2. And then you'll figure out that answers x as some answer A and B right there. And that's how the quadratic equation can be put to use there. And there's actually 2 ways that you can solve this, right? You have the method via factoring, and then you can solve for x from there. So let me put the 0. So there's the method via factoring with the x method that you might have learned a bit ago. And if you can't really factor it out using the x method, that's where the quadratic formula would take place as well. So oftentimes you'd want to factor first and then use the quadratic formula afterwards. So yes, there was actually these application problems we were going to go through, but there wasn't really much time for it. So like Sherry said, she will send you the problems in addition to the worksheet problems as well. So don't worry too much about reading them. She'll have you send the problems into a Gmail file. So that's it with this lecture. As usual, we have these additional resources that we would like to direct you to, right? Hippocampus, Khan Academy, the Learning Lab, and of course our online Learning Academy, in case if you're having trouble with any of those problems. So that'll be it with quadratic equations and stuff. We'll have our last seminar on function.